Professor Jiangong You from China. He got his PhD at Peking University, and right now he is a professor at CERN Institute of Mathematics. He has made very significant contributions to the study of quasi-periodic cocycles, the problem of reducibility, and applications to one-dimensional Schrödinger operator.
Okay, thanks for the introduction. Okay, it's my great pleasure to have a chance to give a talk in this big event. And today, I'm going to talk about a special theory for a special kind of dynamical systems. The theory is called almost reducibility, and we will use it. We will apply it to the study of Schrödinger operators. Okay, I will consider a special kind of dynamic systems defined on cylinder, and TD is the d-dimensional torus. Course R2. R2 can be any Ra. And the dynamics, this TD, the torus is called base. And this R space, the Euclidean space, is called fiber. And the dynamic systems defined on this spatial manifolds, it looks like this one. And the dynamics in the base is just a rotation. And the dynamics in the fiber depends on the base, and it's linear. And this matrix for R2, the matrix is two-dimensional. This is of this spatial form. This kind of dynamic systems is called Schrödinger cocycles, quasi-periodic. And sometimes we can consider more general case, say we can assume this matrix is in SL2. And even in SL A, and if A is in SL2, we call this cocycle quasi-periodic SL2 cocycles. So this is a special kind of dynamic systems. And we are also interested in the continuous counterpart, that is quasi-periodic Hill's equation. It's a differential equation of second order of this form. Certainly, this equation is equivalent to this system. So this is a linear system, but non-autonomous. And today, I will focus my attention on discrete case, that is cocycle case. Okay, this is high dimension. So now I introduce the concept of reducibility. Given a linear system or given cocycle, we say it is reducible if you confine a change of variables, keep the dynamics in the base, which transforms the original cocycle to a constant cocycle. You know, before A is dependent on theta, and after the change of variables, the transformed dynamic systems is constant. That means C is a constant. It's equivalent to in continuous case, to find a matrix B so that this is satisfied. In the discrete case, we try to find a B so that be defined on torus so that this is satisfied. If this is true, we call this cocycle reducible. And there's a classical result due to Floquet. It's called Fleck theory. That means if the system is periodic, that means the frequency is just one in continuous case, then the system is always reducible in the sense I introduced before. And certainly the quasi-periodic cocycle is a generalization of periodic one. So natural question is, if for case 0 remains true for quasi-periodic cocycles. That means the components of the frequency is bigger than 1. Unfortunately, this is not true, and there are some obstructions to reducibility. One obstruction is the so-called non-uniformly hyperbolicity. And if a system, in linear system, is non-uniformly hyperbolic, then it's definitely not reducible. Even the system is uniformly hyperbolic, then we still, to get reducibility, we still need to have some arithmetic condition on the frequency omega. And also for the rotation number, I didn't introduce now. And anyway, omega, this notation has been introduced by Raphael in last talk. And okay, sometimes reducibility is not available, so we need to introduce some concept which is weaker than reducibility. We call it almost reducibility. And almost reducibility means instead of find a change of variables to transform the system to a constant, we try to find a sequence of change of variables, BA. We try and find a sequence of BA so that this BA sends the original system to a system which is arbitrarily close to a constant 1. That means this BA satisfies this equation, and here CA is a constant, and FA goes to 0 when A goes to infinity. And if you can find a sequence of BA satisfies this, then we say this cocycle or this linear system is almost reducible. Usually, BA will not converge, will blow up when A goes to infinity. In some cases, certainly if BA converge, then it's actually there's no difference between this case and reducibility. Anyway, almost reducibility is a concept which is weak than reducibility. Sometimes in application, we need more. We call it quantitative almost reducibility. That means we not only need to find a BA which satisfies this so that FA goes to 0, we also want to have estimate on the normals of BA and normals of FA in this way. And so we want to know the decay rates of this quantity. Usually in the application, people expect the exponential decay. And sometimes we need to know, in some applications, we need to know the structure of this constant matrix CA. Okay, and reducibility has been extensively studied because of the background of application in the spectrum theory of quasi-periodic Schrödinger operators. And there are a lot of advance has been made during the past maybe 40 or 50 years. And the first result was due to DW Sidai and then Eliasson that developed the so-called perturbative reducibility. And also the generalization is non-perturbative reducibility, which is semi-global, is not that local, okay? And by Avila, Fayad, Karakrin, they are in the audience, and Ho and myself, and also almost reducibility and rotations reducibility. And then that is global reducibility. Global reducibility means the cocycle or the matrix is not necessary to be assumed to close to constant. And this kind of result we call global reducibility, which was developed by Raphael Krikorin and Avila Krikorin and Avila. And among them, there's big theory called, big problem called almost the reducibility conjecture, which is solved by Avila. And I will briefly introduce a few results along this line. The first result I tell you is due to Dynamical. And I forgot to say, I always assume B theta here is a function defined on torus. It's continuous, it's analytical. So this being as a function of theta is very good. It's analytical. And epsilon is a small parameter, okay? A is a constant. We can see the linear system of this form. And what Dynamical proved, if omega is assumed to be definite, and then if epsilon is small, the smallness depends on certainly on A and B, and also depending on omega in their results. If epsilon is sufficiently small, then this system is reducible. And not for all A, but for typical A in measure sense. In measure sense, that means for a big measure of A, the system is reducible if epsilon is small. And this one result due to Eliasson, who proved more. The assumption is same as Dynamical, and what they get is more. That's why they assume omega is also definite. Then they prove if epsilon is small, and the system is reducible for almost all A. Here is for typical A, for A in a positive measure set. But here is almost for almost all A. So this result is stronger than this one. And so I want to say the results are called perturbative because epsilon depends on the definite constant of omega that depends on gamma and tau. For some, if for some omega the gamma is very small, then the perturbation must be very, very small. So for this reason, we call this result perturbative. And the people are expected to have some results stronger, which is called non-perturbative reducibility. That means try to prove a result so that epsilon does not depend on the definite constant. So if this is true, and unfortunately this is not true, Borgen has a counterexample. In the discrete case, if the frequency is, the components of frequency is bigger than 2, then in the continuous case, if the components is 3, and one cannot expect non-perturbative reducibility. So that means Eliasson's reducibility result is optimal if omega is of high dimension. However, Puig, Vida proved a result, non-perturbative result for Schrödinger cocycles. If this is a discrete case, if the frequency is just one component with single frequency, in this case, people can expect a non-perturbative result. And I want to remark that their proof is indirect. They use Anderson localization and they use dual and get this kind of reducibility. So their proof needs to assume the Schrödinger structure. And so does not fit to general case. So what we prove is this result. We also consider this system. What if we prove is, this is non-perturbative results for this SL2 cocycles, SL2 systems. So the result is the following. If epsilon is small, then the reducibility, the system is reducible for almost all A and all different thing. Before, here is just, you have to fix the different thing, and the smallness of epsilon depends on this given frequency. And so this result is stronger if the frequency is of two components. And the result holds true for one frequency quasi-periodic SL2 cocycles. And so this one remark says that there are examples showing that one cannot expect the reducibility for all A. For all A and all omega, they are counterexamples. So that means this result in some sense optimal. And now I switch to the almost reducibility. If you check this result, I got the result for almost all A and all different things. This is a full measure. So that means the result is true for almost all A and almost all omega. And if you try to find a result for all A and all omega, then the result should be a little weak. So that is almost the reducibility. And we have a result saying that if epsilon is small, then the system is almost reducible. Now, for all A and all omega. And moreover, there is a precise estimate on that. So at the moment, you cannot see the importance of this estimates. Actually, in the application, we need that. For example, it's decays to zero, this quantity, exponentially when omega is different thing. So the early results was obtained by Eliasson, that is the perturbative version of this almost reducibility. Now I switch to the global reducibility. This problem is called almost reducibility conjecture. So after we cannot expect almost reducibility for all A because there are some cocycles which is non-uniformly hyperbolic that cannot be almost reducible. And however, in one frequency case, Avila introduced a concept called subcritical. That means the cocycles or the fundamental solutions, this control of the growth, and then prove the following almost reducibility conjecture that says if alpha is irrational, not necessary to be different thing, A is in LCR2, then this cocycle is almost reducible if and only if it is subcritical. So subcritical is equivalent to almost reducibility. So this is the almost reducibility conjecture which was solved by Avila. And one remark is subcritical cocycles are not necessary to be close to constants, not like the results I mentioned before. All the results is close to the constant, but here it's not necessary. And this is the reason why we call this kind of global, this result global reducibility. And previous to this result, they already have some global results given by Raphael Kirkoring and Avila Kirkoring. And the second remark I want to say is, since theory is a beautiful theory, but since the theory is global, and there is no very optimal control on this quantity, so in the local case, people can do that. So in the application, people have to combine this global result and more refining the local results. Okay, and now I want to switch to the applications of this kind of reducibility theory And the application is for Schrödinger operators. Okay, Schrödinger operator is an operator defined on L2, L2Z, and of this form. So this is a linear operator, and VA in here is a sequence of numbers, real numbers, and usually bounded. And then this is a bounded operator. And we are, in fact, interested in the so-called quasi-periodic Schrödinger operators. That means this VA is defined in a spatial way of this form. First, give a function defined on TD, in D-dimensional torus, and given alpha rationally independent, we write VA in this way, and we put VA in here, we got operator. We call this kind of operator quasi-periodic Schrödinger operators. So this is the subject. This we are interested in. And certainly you can consider the continuous counterpart of the Schrödinger operator. This is differential operators. And I will not talk about this today. And in the discrete case, there's one quasi-periodic Schrödinger operator which is of particular importance. That is called almost material operators. It's an operator which is very spatial. You see the potential, this is called potential. The potential here is just a sine function, and with some parameters, lambda, and there's alpha here and theta here, 3 parameters. And all the parameters has a very concrete physical meaning. And usually, lambda here is called coupling constant. Alpha is called frequency, and theta is called phase. And I want to say that almost the material operator is the exact mass model for integer quantum Hall effect. So this is not an approximating model, it's an exact model. So this is the reason why people are interested in these particular operators. Okay, so I will focus my attention to this one. Certainly, reducibility result can be applied to more general operators, but I will focus my attention on this. And given operator, so we are interested in the spectrum of this operator. This is an operator here. Certainly, we can define for a given operator in a standard way the spectrum. And we assume this is a real function. This is real. So this is in this case, this is a self-adjoint operator, also bounded, because this is a bounded sequence. And this is a bounded self-adjoint operator. So the spectrum of this operator contains in a bounded segment in R. So all the spectrum are real. And it's a closed set. And when alpha is irrational here, if alpha is irrational, then the spectrum is a perfect set, which means the spectrum does not contain any isolated points. And also, the spectrum set itself is independent of theta when alpha is irrational. If alpha is rational, then this set is dependent on theta, but if alpha is irrational, it's independent of theta. Okay. And also, we are interested in the spectral measure. So for a given operator, you can define spectral measure in a standard way, and we get a measure on real line. So we get this measure. And then we can make decomposition with respect to the Lebesgue measure, and we have then there naturally have 3 parts. One is absolutely continuous with respect to the Lebesgue measure, and the second part is singular continuous, and the third part is pure point. And different from the spectrum before I say, if alpha is irrational and the spectrum is not sensitive to theta, but spectrum's measure itself, the nature of the spectral measure may depend sensitively on theta, okay? I will come back to this later, okay? And this is one measure. If you take an average, we can define a function of the energy E. This function is called the integrated density of states. And also, people are interested in the so-called Anderson localization and the dynamical localization. So, given operator, we say this operator display Anderson localization if H has pure point spectrum. That is, the spectrum measure is purely point, and also the eigenfunction decays exponentially. If this is true, we say this operator has Anderson localization. In fact, physicists ask more, and Anderson localization is not that precise for physicists. They actually need the following more stronger one called dynamical localization, which means if you give your initial data, then this is a solution of the linear Schrödinger equation with initial data phi. And if the initial data is localized, and we hope that the solution is localized for all t. If this is true, then we say this is a dynamic localization. And now the issue in the spectrum theory certainly is we are interested in the spectrum set itself and also spectrum measure, and also Anderson localization and dynamic localization. In some cases, such as almost material operators, there are physical parameters in the operator, then we are interested in the phase transition. Okay, now I want to say quantitative almost reducibility provide a powerful tool to the study of all the above problems. So I will choose some of them to introduce. And one result I want to introduce is the so-called dry-time problem for in non-critical case. That is result by, with Avila and Joe. And the second result I want to introduce is the so-called Jiangong conjecture that is on phase transition of almost material operators. This is a result, also a result with Avila and Joe, which has been published. And if I have time, I will introduce the third one, exponential dynamic localization of almost material operators. That is, I joint work with my students, Go and Joe. Okay, certainly this reducibility has more applications, but I don't have time to introduce. So now I introduce the first one, that is so you know this is almost a material operator. Then there's a problem called the dry-time problem, which asks us if the spectrum I've said is a closed set. Let's ask if this set a contour set. So this kind of problem is also called Asper conjecture, and this Asper is a physicist, Russian physicist. Okay. And there are numerical results by Hofstede which suggests the conjecture is true. So this is a picture for the diagram for the spectrum, and there are many people worked on this problem, including Belizard, Simon, Sinai, and many others. And finally, I want to say this result was completely solved. And first of all, lambda equal to 1 case by Avila and Krikorin, and the final result is given by Avila and Mikaya. And the side 10 problem is true for lambda is not 0, because lambda 0 equal to 0 is a trivial case, so you just ignore that. Then the spectrum is a contour set. That means the trithetic, okay, this result completely solves the tritheticity problem. Now I introduce formulate a stronger version of this thematicity problem, which is called the tritheticity problem. And to formulate the tritheticity problem, we have to introduce so-called the gap labeling. So what is gaps? Gaps is each maximum open interval in the complementary of a spectrum is called a gap. So they may have infinitely many gaps. And IDS I've defined before. This is a result by Jones and Moser, citing that for a given gap, then IDS is a local constant of this form, of this spatial form. This is a fractional part of A in alpha. And in the operator, alpha is fixed, so that means each gap is assigned an integer A. So this A is called labeling. So there are several different definitions for the gapping, for the gapping. And another one is use terminology of differential geometry. So in physical literature, people call this a chain number because it's defined as a chain class. Okay, I want to say IDS for people familiar with dynamic system. IDS is nothing but the rotation number. It's just the rotation number. Okay. And this picture of this rotation number is non-decreasing and constant in the gaps. If there's a gap here, it's a spectral gap, then the rotation number is a constant. If there another gap, then here is another constant. And this function is non-decreasing, so the picture looks like this. If there are infinitely many gaps, then you see a Davis staircase. Okay, and in 1981, Marco Case posed the following question for almost material operators: aside whether or not the inverse of the gap labeling theorem is true. That means are all gaps open for all irrational alpha and all lambda is not 0. If I go back to this picture, that means given a k here, you find a number here, and then you draw a picture here, draw a line, then the problem is they must intersect this graph in a segment, not just a point. So this is the problem. So if you can prove this result, then automatically you prove the spectrum is a Cantor set. So in this sense, dry thematicity problem implies, so it's stronger than thematicity problem. So Katz problem, this is the Katz problem. And in physical literature, this is also called the thematic conjecture. And there are a lot of results. If you try to prove that, you have to assume some conditions ask some arithmetic properties of alpha. That's kind of Diophantine. And also, if alpha is not Diophantine, you can define number beta, use the fractional expansion of this alpha, and define this number this way. And this beta measures how far this alpha is from the rationals. And if beta is bigger, then this is very Liouvillean. That means it's very close to rationals. And there are some long results on dry thematicity problem. One is by Choi, Elliott, and Su. Let's assume beta is infinity. Beta could be infinity. That means if this frequency is very, very Liouvillean, then the result is true. And the second result I want to mention is due to Pooch, and he proved the result assuming alpha is Diophantine and lambda is sufficiently small. And the second result is proved by Vila and Jinskaya saying if alpha is Diophantine, then the result is true for all lambda but 0 and plus and minus 1. And if alpha is Newtonian, if lambda is in this interval, then the result is also true. So then you see the picture here. This is the two parameters. This is lambda and this is beta defined by alpha. And the dark place is solved previously, and also the points in this line, in this axis is also solved. And here is not solved, and here is not solved. And what we proved is this one. Use quantitative almost reducibility, we can prove this result. The dry-mathematic problem is true for all lambda but 1. And the remaining case is lambda equal to 1 and alpha is definitely somewhat like that. Beta is 0. This is the remaining type. Okay. That means we feel or this part, but only left unproved is this point. Okay. This is one result I want to introduce. Now you can ask a further question. We already proved all the gaps are open. Then you can naturally ask how big are gaps. And this result by Leguer, with Leguer and Zhao and Zhou. Martin Leguer is in the audience. And we suppose alpha is definitely, then we can get this kind of very beautiful asymptoticals for the gaps. So we assume this is a gap. GK is a gap with labeling K. And then with this this is the length of this gap because it's a segment. This length take a line and divide by K. Take a limit, it is exactly line lambda. There's tyro here, there's low minus here. So because we assume lambda is smaller than 1, so it is negative. That means the length of the gap decreases with the labeling exponentially, and the exponential rate is exactly 9 lambda. So this estimate is very precise. And before there are many results on the upper bands and by many people. So I don't think I have time to introduce. And the second result I want to introduce is the phase transition. So this also for almost the material operator. This conjecture okay. So from here you see, if lambda is 0, this is a free Laplacian. Then the spectrum measure must be absolutely continuous. If lambda is very big, then this is a tight binding model. So physicists now usually is a pure point spectrum. So if you let lambda increase from 0 to infinity, then the nature of the measure changed from absolutely continuous to pure point. So where is the point of change? The point is called phase transition point. So Aubrey-Andre conjectures that the transition point is in lambda equal to 1. He conjectured lambda is smaller than 1, then the operator has purely absolutely continuous spectrum. And on other hands, if lambda is bigger than 1, the spectrum is pure point. So then they conjecture lambda equal to 1 is the unique phase transition point. And but unfortunately, this conjecture is not very precise. Avron and Simon give a counterexample. He found a particular alpha so that this conjecture is not true. This particular alpha is very Liouvillean. So their counterexample suggests that you have to take alpha into account. And however, the Jeremiskaya proved the following settles this conjecture in measure sense. That means he proved if you assume alpha is definite, then the result is true. Then the result is true. The conjecture is true. And almost assured. Here, say for almost all theta and almost all, okay, for almost all theta. And so you see for defining alpha, number equal to 1 is exactly the unique transition point. And Jiangong has a conjecture for Newtonian alpha. That's like, if alpha is Newtonian, then you can define beta by alpha, which is usually positive. And that's like, if lambda is bigger than 1, smaller than e2 to beta, then the spectrum is purely singular continuous, and otherwise it's pure point with Anderson localization. And so you see for Newtonian alpha, there is another phase transition point set here, e to the beta. And we prove this is true. And for all lambda irrational, and for beta is here. For beta is infinity, it's purely singular continuous. It's already known. And this is a result by Vida. So if lambda is smaller than 1, then the spectrum is purely absolutely continuous. Then this result is stronger than Jiangong because there, she gets the result for almost all theta. And another result, it's result with Vida and Zhou. Let's say it's exactly the Jiangong conjecture. And if you look at this picture, the system contains 2 parameters, and you see in this region is pure point, this region is purely singular, and this region is purely absolutely continuous. And so still have some minutes. I go to the third part of my talk, that is exponentially dynamical localization. And I've said before, dynamic localization means initially localized web packets keep localized under Schrödinger flow. That means it's always localized for all t. And there are many different definitions for dynamic localization. But the strongest one is the following, called exponential dynamic localization in expectation. That means, this is the solution of the Schrödinger equation with initial delta L. Then this is the n components. Because this is it's not uniform in theta, then we take integral with respect to theta, then we say this is bounded by this kind of exponential small quantity centered at L. And with gamma here is localized rates. And there are many people consider this kind of problem use other measures by Eliasson, by Bogen, Goldstein, and Schlag, and Jiangong. And their result applies to this case. Usually they can prove Anderson localization. I already mentioned that Anderson localization is weaker than exponential dynamic localization. And for almost material operators also, there are a lot of results on that due to Jiangong last, Geminate and Jiangong and the others. And I mentioned here, the third result here is the proof for this AMO. And if alpha is defined, lambda is bigger than 1, it has an exponential dynamic localization. So this is the only result on exponential dynamic localization. And now I want to say they didn't have estimate characterization on the localized exponents. So what we get is a bit more. So this result with Go and Zhou. And assume alpha is defined and lambda is bigger than 1. This is a standard assumption. then this operator has exponentially dynamic localization with localization exponent non-lambda. Here we find the exact localization exponent. So this is optimal. And okay, now I want to still spend 1 or 2 minutes to give a summary. And I introduce you a quantitative almost reducibility. This is a spatial theory for a spatial family of dynamic systems. It's called linear, quasi-periodic linear systems or quasi-periodic cocycles. And this kind of theory is a power tool for the study of the spectrum of quasi-periodic Schrödinger operators. And I only mentioned 3 results. Actually, there are quite a lot of them. Yeah. And the direct application of almost reducibility is a spectrum theory for small potentials. That is the work by Dynamical and C9 and Elias. And actually use operator. I didn't introduce this operator. It can also be used to study the spectrum theory with for operators with big potential, which corresponding to non-uniformly hyperbolic cocycles. So the final sentence is we believe this kind of method, this kind of almost reducibility, quasi-periodic, quantitative almost reducibility can be used to study, if not all, almost all problems in the spectrum theory of quasi-periodic Schrödinger operators, certainly in 1 dimension. So my time is out, so I want to stop it here. Thanks for your attention. Thank you.